Hello everyone, and welcome to Lecture 11. So what we'll be doing today is mostly review. In fact, specifically what we're going to be doing is first we're going to start by reviewing the new rules for our first order logic natural deduction system. We'll just go through these quickly, again as a kind of reminder. Then we'll talk a little bit about the proof theoretic concepts for our first order logic natural deduction system. These are going to be the same as the ones we used for TFL, so again, we can go through these quickly. Finally, what we'll do is talk about proof theoretic concepts and the relationship to semantic concepts. This will really be the bulk of what we're going to talk about for this lecture. There'll then be a second video. Now, this second video is going to start in on the topics of metalogic. And metalogic is reasoning about the nature of our formal systems, about our logical system. Now, this video is going to be entirely supplementary. It's in fact going to talk about stuff that you won't actually be asked to read until next week, but I thought it would be good to go ahead and get it out there in case you're interested, you can watch it. Now, with regards to the metalogical stuff, what we're going to do here is it's mostly information that I think you should know. It's not necessarily things that I'm going to examine you on. In fact, there'll be one specific part that I'll flag up that I will in fact include in the examination. It'll be in a part in lecture 12. So if you're running out of time or you don't have it or you're not really inclined, feel free to skip the video on mathematical induction. But that's going to be the plan for today. We'll do some review, and then there'll be the supplementary video on mathematical induction. So let's get started. So as I said in this first video, what we're going to do is just review our FOL natural deduction system. And the place to start is with our new natural deduction rules. So, of course, the bulk of our rules here are just about how we can play around with our quantifiers. The first rule we'll use is a very simple one. It's universal elimination. And the idea here is if you have a universally quantified formula, you can replace all the variables associated with the universal with any name you like. The only restriction here is that you have to replace every occurrence of the variable with the same name. You can't pick and choose. You need to replace every occurrence of the variable with your name. And note that this sentence you're doing the replacement with could be in the assumptions, it could be something you've derived, it could be something that you started a subproof with. All that matters is that this sentence is somewhere above where you want to do your substitution on your proof. So I think probably universal elimination is one of the easiest of the new rules. It's very simple to use, there's no restrictions. A slightly more restrictive one is universal introduction. Universal introduction is where we can take a sentence featuring a name, replace every occurrence of the name with a bound variable attached to a universal quantifier. So we're introducing a universal quantifier. Now the restriction here is that the name we're replacing must be arbitrary. And what this really means is that the name we're replacing can't occur in any undischarged assumptions. So this sentence can't appear in the list of assumptions we have at the beginning, nor can it be, if we're in a subproof, in the sentence that we started our subproof with. Relatedly, the variable we're going to use cannot already occur. That's just because we want to avoid any clash of variables. And finally, just as with elimination, every occurrence of the name needs to be replaced with the relevant variable. The biggest issue here is, again, this requirement that the name we're replacing needs to be arbitrary. So this will often mean that the name you're using just simply can't appear in any assumption that you've had so far. So that's universal elimination and introduction. Let's talk about the existential. Existential introduction is also a very easy one to use. The idea here is that, right, if you have a sentence featuring a name, you can replace occurrences of the name with an existentially bound variable. The only real restriction here is that the variable you're going to, or the variable you're going to introduce can't already appear in your sentence. And that's again just because we're trying to avoid clash of variables. The really nice thing about existential introduction is that you can pick and choose. So, for example, if we were taking our sentence here and it has two occurrences of the name, we could replace just one occurrence, or we could replace the other occurrence, or we could replace both with regards to an existentially quantified variable. So, existential introduction is even more flexible than universal elimination. Now, unfortunately, existential elimination is even more restrictive. In order to use existential elimination, what we need is an existential sentence, and we then construct a subproof involving an arbitrary name that we'll use as a substitution instance. Then, within the subproof, starting with this substitution instance, we derive some result. Importantly, the result we're going to derive cannot feature the arbitrary name. But we can then, if we've shown that this result B follows from our existential substitution, we can say that this result is a product of the existential. So the restrictions here, there's quite a few. First one is that, right, if we're going to use some name in order to ensure it's arbitrary, just like with universal introduction, we have to make sure that the name we're using doesn't occur in any undischarged assumption before we start our subproof. So this is to ensure that the name remains arbitrary throughout. Secondly, the name can't appear in the existential that we're using, because if it does, we already know something about it and it's not an arbitrary name. Finally, whatever result we get out of our subproof, our arbitrary name can also not appear in it. Again, this is to ensure that we're entirely throughout the subproof treating this name in an arbitrary fashion. If we ever have anything particular about it, so that it occurs in our initial one, or it's in some undischarged assumption, or it's in the result, we're not good. What this means is that a lot of times when we're doing our existential eliminations, what we'll do is derive a sentence featuring a name, and then we will do existential introduction to replace that name with an existentially quantified variable. So weirdly, many times when you do existential elimination, your result will in fact be a sentence featuring an existential. And that's slightly strange, but again, remember that elimination really is just better understood as something like derivation. So those are our four main rules. We also have a few other ones. So four that we have that are actually supplementary rules are quantifier conversion rules. And these are ones that let us move a negation inside or outside of particular quantifiers. Now, the thing to note with regards to these is it always has to have the quantifier or the negation as the main operator. So in this case, right, on our leftmost operator. If you have that kind of a setup, you can then use the quantifier conversion rules to play swapsies. And this can be handy if, for example, you want to do something like universal elimination because it's easy. Or you want to, say, derive something that you then could use negation elimination to generate a contradiction. The other block of rules that we have to do with the identity predicate. An identity is, as we already talked about before the midterm, identity is special. And in fact, identity has special rules. So we have identity introduction. Identity introduction is very, very simple. It's basically at any time you can introduce the fact that some name is identical to itself. You don't need anything. You can just simply stipulate that this is the case. Now, I know I've mentioned a few times in tutorials and things where when we're doing proofs for theorems, 99.9% of the time we'll open with a subproof. The 1% of the time when it's not is because we'll start with identity introduction. Because it's one of the few where we can literally generate a sentence from nothing at all. Now, identity elimination, on the other hand, is effectively really just substitution. And the idea here is that we know an identity statement, so A is identical to B, and we have some sentence featuring A, we can use identity elimination to replace every occurrence of A with B. And what's nice is we don't actually have to do every occurrence. So you can do some or all of the instances of a name with identity elimination. This is handy because it means you can play swapsies a little bit. So that's identity introduction and elimination. And in fact, that's all of the new rules for FOL. Right? And of course, we'll use the old rules that we had from TFL. We'll inherit those, but that's basically it. So the other stuff that we'll inherit from our natural deduction system for TFL are the proof theoretic concepts. So just like with TFL natural deduction, we'll say that a sentence A is a theorem if and only if there's a proof for that sentence from no assumptions whatsoever. So to show that a sentence is a theorem, you construct a proof for it, starting with no assumptions and ending with the sentence you wanted. So that's theoremhood. A second proof theoretic concept we'll have is provable equivalence. We'll say that two sentences A and B are provably equivalent if and only if they can be proved from each other. So to show that some sentences are provably equivalent, you construct a pair of proofs. One that starts with our sentence A and derives B, and then a second one that starts with B and derives A. So note, right, if you're asked a question about these, you have to give two proofs. And our third notion is that of being jointly contrary. So we'll say that some sentences are jointly contrary if and only if we can take them as assumptions and derive a contradiction. And note, importantly, this contradiction will be on the main proof line. So in effect, what we're proving is that our starting assumptions must not all be true together. If they were, we would get a contradiction. So again, these are the same proof theoretic concepts we had before. And we use the same mechanisms or approaches to figure out whether sentences have them, just like we did with TFL. Now, of course, what we've talked about so far really only helps us with some things. Because suppose you wanted to show that a first-order logic sentence is not a theorem, or that two FOL sentences are not provably equivalent, or that some FOL sentences are not jointly contrary. Well, what would we do? We can't really use our natural deduction system because, if you recall just what we were talking about a second ago, all I told you was how to show that it was a theorem, or that they were provably equivalent, or that they were jointly contrary. In fact, if we tried to use our natural deduction system, we'd need to somehow do some reasoning about every possible proof that we could construct. And it's not really clear that we're in a position to be able to do that. We certainly couldn't use our system to do that. So how would we go about showing these things? Well, here is where we come to the relationship between our proof theoretic concepts and the semantic concepts we talked about at the end of the first half of the course. And this is really where we're bringing together everything that we've learned so far to actually give us a full logical system. So the key really to all of this is going to be our single turn style and our double turn style. So if we think about our single turn style, right, we've defined it in terms of provability. So we can say that, right, some sentences single turn style C, if and only if there's some proof that starts with these as an assumption and then ends with C. Now, with regards to our double turn style, it kind of played double duty for us. We had one conception where it was tautological entailment, and then we had a second conception when we thought about FOL, where it wasn't just tautological entailment, but it was logical entailment. So, what does it express then? Well, if we're thinking about it in terms of FOL, it says there's no interpretation that makes these sentences true and this sentence false. Now, these are clearly related, but they're different notions. This one, if we're thinking about FOL, has to do with the existence or non-existence of interpretations, whereas this one has to do with the existence or non-existence of proofs. Now, the tight connection between the two, and this is the real beauty about our logical system, is that they're extensionally equivalent. That is, some sentences, A1 through AN, will prove C if and only if there's no interpretation that makes all of the sentences true and C false. This is the real key. And the neat thing is that once we have this relationship, then all of our conceptions, all of our proof theoretic and semantic conceptions are going to line up, such that we can say an argument's valid if and only if the conclusion can be proved from the premises using our natural deduction system, or that two sentences are going to be logically equivalent if and only if they're provably equivalent. Right? And finally, we're going to say some sentences are jointly consistent if and only if they're not jointly contrary. So really what we're getting is that the gaps that we had in our natural deduction system and the gaps that we had in our interpretations cover each other. So we can actually see this if we think about what we can do. The really cool upshot is that no matter what we're doing, we can always use the easier tool depending on what's more convenient. So we're asked, right, is a sentence a tautology or a logical truth? Well, if it is, we can construct a proof, show it's a theorem. If it's not, we can offer a valuation or an interpretation if it's in first order logic. We can give a counter model to show that it's not a logical truth. Similarly, to show a sentence is a contradiction, what we can do is construct a proof for its negation. That is, we show its negation is a theorem, and then we know that the sentence could never be true. Meanwhile, if we think that it's not a contradiction, what we can do is we can offer an interpretation that makes it true. Finally, or not finally, similarly, if we wanted to show that two sentences are equivalent, right, what we can do is we can offer a pair of proofs and show that they're provably equivalent. On the flip side, if they're not, we can offer a counter model, an interpretation that makes one sentence true and one sentence false. If we're thinking about consistency, right, to show that some sentences are consistent, what we can do is offer an interpretation that makes them all true. Or if they're not, we can offer a proof to show that they're jointly contrary. And finally, and the big one, we finally have the FOL tool. If we're asked whether an argument's valid, if we think it is, we should be able to construct a proof that starts with the premises' assumptions and ends with the conclusion. And if it's not, we can construct an interpretation that makes all the premises true and the conclusion false. So our full kind of logical system is our natural deduction story and interpretations married as one. And that's incredibly cool and really powerful, because now once we have both in our hands, we can kind of do anything we want. We have all the power in the world, in some sense. That is, we're finally in a position to actually answer the stuff that we started with. We've got a full tool now to assess whether arguments are valid or invalid. And it's really powerful. It took us a long time to get there, but we got there in the end. So that's the real neat thing about taking this natural deduction stuff and the interpretations together. We're finally now in a position where we can check out everything we want. And it only works because the two relate to each other. Now, of course, the problem is actually proving that. So I've told you that single turnstile and double turnstile are extensionally equivalent, but it's very difficult to show that they are. To show that they are, we'll need to prove the soundness and the completeness of our logical system. So the soundness shows that all theorems are tautologies. Effectively, that says, right, if the single turnstile holds, then the double turnstile holds. And completeness shows that all tautologies are theorems. That is, that if the double turnstile holds, then the single turnstile holds. What we're going to do in lecture 12 is we're going to answer this question. We're going to try and show how it is that the single and the double turnstiles extensionally agree. Now, importantly, what we're going to do is we're going to do this for TFL. We're not going to cover it for FOL. That's primarily because it's hard enough with TFL. It's extremely difficult for first order logic. And arguably, the move here to proving soundness and completeness is where we start to leave introductory logic behind and we get into intermediate logic. So, what we're going to talk about next week is we're going to start by thinking about a general mathematical tool that we'll call mathematical induction. Now, this will be extremely useful. This is helpful for proving soundness and completeness, but it's also just a handy process and a tool that you probably should know how to use. We'll also talk about substitution and putting sentences in what we'll call normal forms. And we'll also finally talk about what we'll call expressive adequacy. So this has come up in discussion a few times, but why don't we have certain rules or why don't we have certain connectives? For example, why do we need the biconditional? It seems pretty clear that we could get by without it. We could just use conditionals and conjunction. So what we're going to do with regards to expressive adequacy is think about how many connectives do we really need? Could we get by with just two? Maybe even one? So again, the move here is going to be pretty significant. The difficulty curve is going to ramp. Now, I want to make it clear that the stuff we're going to talk about here, it's really going to be me kind of lecturing at you. And the idea isn't that I want to necessarily, force you to prove soundness and completeness. I think that's asking too much. Instead, what I want to do is, I think this is stuff that you should know. So lecture 12 is mostly going to be me talking to you about stuff that I think you should know. There's going to be one bit on normal forms that I'll ask you about in the exam. I'll flag it up. I'll make it very clear. I'll have it its own little video. The rest of it is something that if you're interested, you should watch. If you're not, it's not going to hurt me if you don't. So, okay. So that's really where we're moving now. We're going to kind of move past all of the stuff we've done, which again, we can think of as kind of introductory formal logic. And we're now going to move into intermediate logic and thinking about meta logic, reasoning about the nature of logic. So that's what we're going to do starting in the next video, which again is going to be supplementary. Don't feel obliged to watch it before Q&A for lecture 11. Do try and watch it before Q&A for lecture 12. So thank you guys very much, and I hope to see you in the lecture for mathematical induction.